Factoring special trinomials and binomials. Let's start out by factoring perfect square trinomials. So we've been in the process of factoring trinomials using either the guess and check method or by rewriting the middle term and using factor by grouping. So this here works for particular trinomials that have the form that we're going to look at here. So if we recognize a trinomial as having either one of these two forms on the left. So we have x squared plus 2xy plus y squared, or the middle term could be minus 2xy. Then we could just jump straight to the factorization. So the quantity x plus y squared, or the quantity x minus y squared if there's subtraction in the middle. So I think it's helpful to see what's going on with a little bit of color here to recognize the pattern. So if I have a quantity squared, x squared, in the front, and then in the back I have a different quantity squared, so I have y squared. The middle term is taking that x and y and multiplying them together and multiplying it by either positive 2 or negative 2. So if I can see that happening, then I can jump straight to just taking that x and that y, adding them together as a binomial and squaring that quantity. So let's go ahead and look at an example. Let's go ahead and try to factor x squared minus 8x plus 16 using this technique. So to be clear, we could use just the guess and check method, or we could rewrite the middle term and use factor by grouping, but we're trying to recognize when we would apply this perfect square trinomial formula. So if we notice that the first term is a perfect square, which it is, it's just x squared, and if the last term is plus another perfect square, so I have, in this case, this is plus 4 squared. So I'd have to recognize, I'd have to know that 16 is a perfect square. Then this is a candidate for applying this formula, but I have to check this middle piece. So is this middle term, negative 8x, is that, in this case it'd have to be negative 2, so is that negative 2 times the x value, and in this case the 4 value. So negative 2 times x times 4. So we're looking at the first value and that last value that are squared. So it absolutely is. Negative 2 times 4 is negative 8. So the middle term is this negative 2 and the x and the 4. So this is a perfect square trinomial, and that means that we can go ahead and apply the formula, which is just taking those two values, x and 4, and subtracting them, x minus 4, and that whole quantity is squared. So again, this one might have been pretty easy to do using other methods, but we wanted to apply this perfect square trinomial formula. But now let's look at an example where it's definitely beneficial to recognize the perfect square trinomial to make our life a little bit easier. Alright, in this example we're going to factor 25x squared minus 30x plus 9. And again, we can use our guess and check method, or we can rewrite the middle term and then use factor by grouping, but we want to recognize that 25x squared can be rewritten as a perfect square. So we have 5x squared in the first term, and then the last term can be rewritten as a perfect square. So we have plus, we need that last term to be plus a perfect square, we have 3 squared. So we should check, so we have 5x in the first term, 3x in the last term that's being squared. So we'll check the middle term, whether that's negative 2 times the first term times the last term, each piece that's being squared. And it is, it works out. So if I multiply negative 2 times 5, that's negative 10, times 3, that's negative 30. So we do have the case where we can just jump straight to the factorization, which would be my 5x, and it's going to be minus, because the 30x in the middle is subtraction, so I have minus 30x, so minus that last term of 3 squared. So I have that 5x and I have that 3. so we can just jump straight to a factorization. So it can definitely make our lives easier if we can recognize it. Otherwise, we can use our traditional methods. For part C, we want to recognize that we have a greatest common factor here. So that's the first step in any factoring problem, is try to recognize if there's a GCF to factor it out. And all the coefficients are divisible by 2, and there's an x present in every term. So we're going to factor out a 2x from every term, and we would be left with a 9x squared plus 42x plus 49. And the quadratic that's left over is a perfect square trinomial. So we could maybe see it a little bit better if we rewrite. So I'm going to bring down the 2x again. The GCF is going to come on down. The 9x squared, that is 3x as a quantity squared. So the parentheses are important. 3x is a quantity squared. The last term is a perfect square. 49 is 7 squared. So I have plus 7 squared. And then we want to double check that the middle term is, in this case, it's going to have to be a positive 2 times the first value being squared and the last value being squared. So is it positive 2 times 3x times 7? And it absolutely is. So 2 times 3 is 6, and 6 times 7 is 42. So I have my 7 and my 7, and I have my 3x and my 3x, and in the middle, that's multiplied by 2. So we can go ahead and factor this trinomial right away to be that 3x plus 7 all squared. So we bring down the 3x. It has to be plus because we had a plus 2, and then our 7 came right on down as well. So we can't forget the GCF in the front here. So we're going to have 2x multiplied, right? The GCF is multiplied. When we're factoring, we want all terms that are multiplied together as our answer. This next formula is huge. You're going to see factoring the difference of two squares everywhere. So the difference of two squares means exactly what it says. A difference is subtraction. So here I have subtraction of two perfect squares. I have x squared and y squared. And what this is going to factor to is this first term that's being squared, x, is going to be the first part of each binomial. So I have my x and my x. And as long as it's subtraction, it has to be a difference of two squares, and the second squared in this case is y. I'm going to have minus y, and then I'm going to have a plus y. So we notice that the signs here are opposite. So I have x minus y, x plus y. So the tip here is to look for two terms. So it's the difference of two squares. And we want those perfect squares. So we want 1, 4, 9, 16, 25, 36, etc. This is a list of perfect squares involved. So if we have two terms that are subtracted, that makes it a difference. And these numbers are involved, or if I have variables that are being squared, or we'll see other special cases of this, then we know we're going to be applying this formula here. So x minus y, x plus y. So big part here is that this does not work for a sum of two squares. If I have a sum of two squares, that is actually prime, and we'll see an example of that. Let's jump into some examples. So factor if possible. We have x squared minus 49. So I have a difference of two perfect squares here. X is being squared in the first term. In the second term, 49 is 7 squared. So I have my first value being squared, my second value being squared. So we will apply it directly to the formula. We have x minus 7 and then x plus 7. So we subtract the two terms and we add the two terms. One of the things I'll briefly mention is that the order here doesn't matter. In the sense that multiplication is commutative. So for example, if I had left the answer as x plus 7 times x minus 7, that's fine as well. The whole factor can switch places because multiplication is commutative. The important part is that subtraction is between the two terms in one binomial, and addition is between two terms in the other binomial. In part B, we have 1 over 9 x squared minus 100. So here, 1 over 9 x squared can be rewritten as a quantity squared. So we can rewrite it as 1/3 x as a quantity squared. And then we have minus 100 can be rewritten as 10 squared. So here I have my 1/3 x and then my 10 are the pieces that I'm going to subtract and add together in my factorization. So I'm going to leave my answer as 1/3 x minus 10, 1/3 x plus 10. So this is my factorization. And hopefully you can tell these are quick, we just have to recognize it. In this third example, we have 36x squared minus 25y squared. So it's these perfect square numbers that are the red flag as well as the subtraction. So 36 is a perfect square, 25 is a perfect square. So we'll recognize that this first part is 6x as a quantity squared. The parentheses in this location are important. It needs to be parentheses 6x parentheses squared minus parentheses 5y as a quantity squared. So 5y in parentheses squared. So that I have my first piece, 6x, and my second piece, 5y. And then I will apply the formula so that it's 6x minus 5y, 6x plus 5y. So all of these problems had two terms, let's recognize the pattern, and they were all subtraction between those two terms that were perfect squares in each term. This last one is kind of tricky. A lot of students kind of mix up that it has to be subtraction. It cannot be addition. So they want to apply the difference of squares here, but this isn't a difference. So although I have q squared and although 36 is 6 squared, because it's addition, this cannot be factored. So we say that this is prime. This is prime. So there's no GCF, there's nothing else I can do. I can't apply this formula because it's addition. So this is a prime quadratic. Let's take a look at another example. We're going to factor x to the 5th minus 36x to the 3rd. So here, let's recognize that there is a greatest common factor. So we can factor out x to the 3rd from each term. So I'd have x to the 3rd, and left over I would have x squared minus 36. So the part that's left over can be factored further applying the difference of squares formula. So I have that x cubed in the front, and then I can rewrite this as x squared minus 6 squared. So I have an x squared and I have a 6 squared. So that would factor to x minus 6, x plus 6, and then we'll go ahead and bring down the x cubed that is being multiplied, and this is my final answer for the factorization. In this example, I want to factor 81x to the 4th minus 625. This one is a difference of squares, but it's going to work out a little different than previous examples. So here we do have a difference, we have subtraction, but our first term we're going to write out as 9x squared squared. So the quantity that's being squared is 9x squared, because this exponent would distribute to the 9, so I'd have 9 squared is 81, and x squared squared would be x to the 4th. We'd multiply these exponents, so that's remembering our properties of exponents. And then I'd have minus 625 is 25 squared. So we have our first term is 9x squared, that's being squared, and our second term is 25 that's being squared. So this will factor to 9x squared minus 25 and 9x squared plus 25. So we've applied the difference of squares formula, but we constantly have to ask ourselves, is there anything more I can do? Can I continue to factor? So this first part here can be factored further. So this first part is its own difference of squares. So I can go ahead and rewrite this as quantity 3x squared minus 5 squared. And then I'm just going to bring down the 9x squared plus 25. That's still being multiplied. That's still a factor. Well, now this part here, I would recognize that 3x is being squared minus 5 is being squared. So we'll go ahead and write that as 3x minus 5, 3x plus 5, and then the 9x squared plus 25 comes on down and is being multiplied. So this is my final answer for the factorization. And in this example, we're going to factor x cubed plus 5x squared minus 9x minus 45. So we have 4 terms here, so we should think factor by grouping. So we're going to go ahead and create our 2 groups. And we're going to go ahead and factor out the GCF from the first group, which would be an x squared, and I'd have left over an x plus 5. From the second group, I can factor out a negative 9, and I'll be left with the factor of x and then plus 5 when I divide the negative 9 into negative 45. So the common binomial here is x plus 5, so we'll go ahead and factor that out. So we have x plus 5, and then from the first term we'd have an x squared left over, and then from the second term we'd have a minus 9 left over. So now we have to continue to look and think, can I factor anything further? And this x squared minus 9 can be factored further because it's a difference of squares. So 9 is 3 squared. So I'm going to go ahead and just write 9 as 3 squared directly above it. So I have x squared minus 3 squared. So I'll bring down that first part, x plus 5. And then this second piece will factor to x minus 3, x plus 3. So especially ones like this, we really want to get quick at recognizing this is a difference of squares, so we can quickly recognize that it factors to x minus 3, x plus 3, because of how often that difference of squares comes up in this chapter and in future chapters regarding factoring. Lastly, we're going to look at factoring the sum and difference of cubes. So I have x cubed and then plus y cubed. And I can also consider x cubed minus y cubed. So I have both the sum and the difference of cubes. And the formulas look a little intimidating, so let's take a close look here. So once I find out x and y, the values being cubed, the formula is, first we're just going to add them together. So I'm going to keep the same sign. I had x cubed plus y cubed. I'm going to do x plus y, the same sign. Then I'm going to take the x value and square it. So x squared minus, so I'm subtracting. I do the opposite sign next. So I started with plus, the same sign as the original. Then I switch to the opposite sign. That's subtraction. And then I have x, y. So I multiply the two together. Then plus, I have positive. Then I'm going to have y squared. So the signs have a little acronym to help you remember. It's called SOAP. So since this is addition, I keep the same sign between the first two terms. Then I switch to the opposite sign, so that's subtraction. And always positive is the last term. The last term is always positive. So if I look at this difference of two cubes formula, since it's subtraction, it's the same sign, subtraction, then the opposite sign, addition, and then always positive. So it is a little trickier than the difference of squares formula, but it's just going to take some practice. Let's go ahead and take a look at this example. We're going to factor b cubed, so I have a perfect cube, plus 27, which is also a perfect cube. It's 3 cubed. So I have my b, and my second value is 3. That's being cubed. And then we'll go ahead and apply the formula. So we're going to go ahead and keep the same sign, it's addition. We're going to add the two quantities together, b plus 3. So I have my b value, I have my 3 value, add them together. And then what we're going to have is b squared, and then we're going to switch to the opposite sign. We're going to have subtraction. And then we're going to multiply the two together. So b and 3, so I have b times 3. And then finally, it's always positive, so plus, and then I'm going to have the 3 value squared, so plus 3 squared. So I have that b, and then I have the 3 in the middle and the 3 that's squared at the end. So hopefully it kind of helps you see the pattern. Again, it is a little bit trickier to remember, but with practice it will come. And then here we're just going to clean it up a little bit. We're going to go ahead and simplify. Well, b plus 3 stays the same, and then I have b squared minus 3b. So we put the coefficient in front of the variable, and then plus 9. And then what's nice is that this quadratic, it doesn't factor any further. So this is going to remain b squared minus 3b plus 9. We don't have to factor it further. It does not factor further from the difference or sum of cubes formula. In this last example, let's factor 64n cubed minus 125. So some students might think this is the difference of squares. That's kind of a common mistake because they see two terms being subtracted. But we have to recognize that these numbers here are perfect cubes, and we have n cubed. So we're going to write this as the quantity 4n, so in parentheses, cubed, minus 125 is 5 cubed. So we have the difference of cubes here. Our first part is 4n, and our second part is 5 that's being cubed. And then we'll carefully apply the difference of cubes formula. So we'll start with, we keep the same sign between them. We subtract 4n minus 5. And then we take the first value, 4n, and we square it. So we want to keep it in parentheses. That is important. So I have parentheses 4n squared. Then we change to the opposite sign. So we're going to have addition now. And we're going to multiply the two pieces together. So 4n times 5. And the last sign is always positive. SOAP, same sign, subtraction, opposite sign, addition, always positive. And then we're going to take that last value and square it. So 5 squared. So we have our 4n minus 5. We subtract them. And then we take 4n and square it. Then we multiply 4n and 5, multiply the two terms together, and then square the last term. And at this point, we just go ahead and clean it up a little bit. So 4n minus 5. Here, this is going to become 16n squared. 4 gets squared and n gets squared. That's why it was important to keep it in parentheses. So I have 16n squared plus 20n plus 25. And this quadratic cannot be factored further. So this is my final answer.